We have been discussing about instantaneous center of rotation of rigid bodies with emphasis on planar rigid bodies. So we will we posted a video on that, and this particular video is going to be a continuation of that video. Our discussion is still going to be instantaneous center of rotation and our emphasis is going to be on planar rigid bodies. So we have given the general idea of the instantaneous center. We have talked about how the instantaneous center is an important geometric feature of any rotating rigid body, and how it can be used to understand the general motion of a rigid body, and also to figure out velocities at different points of the rigid body. In fact, we showed how if we know the velocities of 2 points on a rigid body, we may be able to, using geometry, find the instantaneous center if the rigid body is undergoing a combined rotation and translation. So remaining on that topic, we will discuss a case where you can have the velocity of 2 points on the rigid body to be parallel while the rigid body is still rotating. So we will consider that case. So let's say that there is a planar rigid body, and there is this point A, and there is a velocity VA of the point A. Now we know that if the velocity of a certain point on this rigid body is its direction is given, then we can say that the instantaneous, and assuming that the rigid body has got a combination of rotation and translation, we can say that the instantaneous center is going to lie somewhere on this line which is perpendicular to VA, right? Of course, if the rigid body is translating with no rotation, then the instantaneous center will lie at infinity, okay, because the radius of curvature of the path is going to be the instantaneous center is going to be at infinity, because the orientation is not changing of one point on the rigid body with respect to another. Now let us say that the rigid body does have an angular velocity of omega, and that would mean that the instantaneous center would lie somewhere on this point C, where C is such that the distance of A to C is given by the magnitude of the velocity VA divided by omega, right? And this comes from the basic understanding that the velocity of a point is omega cross r, where omega is the angular velocity of the rigid body and r is the vector going from the instantaneous center to the point of interest. So this is basically the distance. The DAC is the distance at which the instantaneous center lies if we know the velocity of a certain point, and if we know the angular velocity of the rigid body. Now, one question that arises is that since we have discussed that the instantaneous center can be found out by looking at the velocities of 2 points on a rigid body and drawing mutually perpendicular, or drawing lines perpendicular to the two velocity vectors, what happens if you, let's say, choose the second point B to be a point on this perpendicular line? Okay, because here if you now go by the angular velocity and the and the distance DAC and so on, you will see that if the point B, if rather the point B is on this perpendicular line AC, then its velocity must also be parallel to VA, because how otherwise would you have the instantaneous center happening over here? If the velocity was in a different direction, then you would have to draw a different perpendicular line, and the intersection of those two perpendicular lines would have happened at a different point. Okay, in fact it would have happened at this point itself, and so the instantaneous center would have been over there, which is not possible because B does have a velocity. So if I choose a point B on this line, then I know that its velocity is going to be parallel to VA. Okay, so VB is going to be parallel to VA. So how is VB, how is VB going to be, or what is the velocity or the distance or the magnitude of the velocity VB going to be? Well, you can see from here that VB is then going to be dBc times omega, or in other words, dBc is going to be VB divided by omega. Right? And you could alternately say that omega is equal to VA divided by DAC, which is equal to VB divided by DBC. Right? And this angle, by the way, is also 90 degrees. So one thing that we can see over here is that if the 2 points A and B are chosen such that they are on the same perpendicular line to the velocity A, then what will happen is that the two velocities are going to be parallel. And if you consider this geometric situation where VA divided by DAC is equal to VB divided by DBC, then what it is saying is that this triangle, this right angle triangle with VA as one of the sides and this right angle triangle with VB as one of the sides are similar. They are similar triangles. Okay, and if they are similar triangles, that means that if I draw a line that joins the tip of VA and VB and gets extended, that line is going to intersect at C. So here we have a method then to find C if you have the points A and B whose velocities are parallel but different. Okay, parallel and different means therefore that the rigid body does have a rotation. So 2 points on a rigid body, when they have parallel velocities but different velocities, it does mean that the rigid body has a rotation, it has an instantaneous center, and the instantaneous center in that case can be found out by joining the tip of the vectors, okay, and extending that line and intersecting that line with the line which is perpendicular to the two velocities. Okay, and in this case you can see that when I have 2 points which have velocities that are parallel to each other, they will necessarily be such that the perpendicular to one velocity will contain the second point. So the perpendicular to A, the velocity of A will pass through the point B where the velocity VB is given. So this is another situation. This is a situation where the instantaneous velocity or instantaneous center can still be found out, but the way to find out the instantaneous center geometrically is a little bit different. And one thing that we observe here is that velocity is proportional to distance from C. So velocity is proportional to the distance from C, and clearly that automatically implies that the velocity is 0 at C, which is supposed to be the case. Okay. Now with that we have covered some of the geometric aspects of the instantaneous center of rotation, and now what we'll do is we'll take a few commonly found cases in kinematics or in dynamics where we use this instantaneous center to our benefit for solving problems. So the first case is where we have a disk rolling on a horizontal surface or a flat surface. You could consider a flat surface, and let's say that the disk is rolling in this manner. The center of the disk, C, has a velocity v, okay, as shown here. Then and assume that the disk rolling on plane without slipping. Okay. Now, if it is rolling without slipping, now let us consider the basics of the instantaneous center. So clearly this rigid body has got a rotation because the orientation of the disk does change. So if we are interested to find the instantaneous center, what we do is, the first things first, we draw a line that is perpendicular to the velocity of the point C, because the velocity of the point C is, we know the direction. So we know the direction of this vector, so we can draw a line perpendicular to it, and that line will be vertical in this case, or perpendicular to the plane, because the velocity is parallel to the plane, and so this line is going to intersect the plane at the point where the disk is also in contact with the ground. Now how do we find the instantaneous center? Well, we make the note that if disk rolling without slipping, then Vp, where P is this point of contact here, Vp is equal to 0. It must be 0, right? So if you consider a fixed ground, okay, we are not considering a ground that itself is moving, but let's say a fixed ground, and the disk is rolling without slipping. So clearly, since it is rolling without slipping, the velocity of the disk at the point of contact P must be 0 because the ground is not moving. So the velocity of the point P is 0, okay, and that then must be the instantaneous center, okay. And so you can see that the angular velocity, so therefore we can say the angular velocity, okay, with which the disk is turning is given by v, the magnitude v divided by r, where r is the radius of the disk, right? So that's a very basic result, and it is used quite frequently in solving problems. Now, one of the consequences of this is that because now we have the instantaneous center, we can predict the direction of the velocity of any point on the disk, okay. So for instance, if I choose a point Q here, it's on the disk, and it doesn't have to be on the periphery. It is at a certain point on the disk, fixed to the disk. So because Q is a part of the same rigid body now, what I can then do is I can say that now I reverse engineered the process. I say that I'm going to draw a line from Q to P, P being the instantaneous center, and let me just point out over here that therefore P is the instantaneous center. Okay, now from the instantaneous center I draw a line to Q, and then perpendicular to that I draw the vector VQ, right? So then I have the direction of the velocity of the point Q just using geometry and my knowledge of the instantaneous center. And in fact, I not only know the direction because it's perpendicular to this line, I also know the magnitude because I know that the magnitude of VQ is equal to omega times the distance P to Q. Right? So if I know the distance, that is if I choose a point on the disk and I know exactly what is the distance of the point Q from the point P, then I can find out what is the I can find out the distance, and then from the angular velocity I can find the velocity of the point Q. So this is a benefit of using the geometric concept of instantaneous center to solving different types of problems. So this is one case where we use instantaneous center in solving problems. I'm going to show a couple more cases. So next, let us consider the case of a rod which is sliding down a wall. So it is resting against a wall and then it starts sliding down at a certain instant. This is a problem that is very standard in kinematics and dynamics. So let's say you are considering a rod that is sliding down. Let's say here we have point A, here we have point B, right? And these are fixed surfaces. Now, as the rod slides down, you can see that this contact point B, which is touching the ground, is going to have a velocity parallel to the ground. So VB is going to be along the x-axis. And the point A, which is touching the wall, its velocity is going to be directed downwards. So VA is going to be in the y direction or negative y direction. Right? So if I want to study this motion, and you can see that the orientation of the rod is changing. So let's say this is angle alpha. You can see that the orientation of the rod is changing as the rod falls. So clearly the rod is undergoing rotation. Now if I want to find the instantaneous center, what I can do is go with the basics, just draw a line that is perpendicular to the velocity A and draw another line that is perpendicular to the velocity at B and let them intersect. Let's call that intersection point C. Okay, and this is then our instantaneous center of a rod. So at any given instant, as the rod slides down, its instantaneous center is given by this geometric construction, and this corner is the instantaneous center. Now the instantaneous center itself changes because as the rod moves you have to, so let's say we consider another instant, a prior instant, let's say, where the rod was like this, right? So here also we can draw the same perpendiculars, because VB was still in this direction and VA was also still in the downward direction, and the instantaneous center was here, right? So the instantaneous center, you can see, is going to change its location. So that's why it's instantaneous, because from one instant to another the center of rotation changes. But if you freeze the instant, if you take a particular instant, you will see some interesting features of the instantaneous center. First of all, the IC forms a rectangle, right? So if I consider the origin as O, OACB is a rectangle, right? And AB, which is the rod, is a diagonal. And this is going to be true at any instant. It's only that the shape of the rectangle is changing as the rod is sliding down. And you can see that OC is the other diagonal, right? So if I join OC, I have two diagonals. Now in a rectangle we know that the point where the diagonals intersect, that point bisects the two diagonals, right, because of the symmetry. So this point of intersection, if I call this Q, AQ is equal to QB is equal to L over 2 if the length of the rod is L. Right? If the rod is of length L, then AQ equals QB is equal to L over 2, and it doesn't matter where the instantaneous center is, the same thing happens over here. So if this is my point O and this is my point Q, AQ is equal to QB is equal to L over 2. So so at any instant as the rod is sliding down, you see that the instantaneous or rather the instantaneous center, yes, it forms a rectangle. And furthermore, you have this scenario where the rod and OC forms the two diagonals of the rectangle, and the diagonals of a rectangle bisect each other. So therefore AQ equals QB is equal to L over 2, and furthermore in a rectangle the two diagonals are of the same length. So you can say that OQ is equal to QC is also equal to L over 2, because this is a rectangle, so the two diagonals of the same length, the two diagonals are bisecting each other, so each of the segments AQ, OQ, BQ, CQ are going to be of length L over 2. And so in some problems you will see that the goal is to find the velocity of the center of this rod, and now you can see that the velocity of the center of the rod is therefore going to be like that, making a perpendicular with CQ. So this is velocity of Q, right? And so you can say then that therefore velocity of Q, the magnitude of it is equal to omega times L over 2, where omega is the angular velocity with which it is turning. And in fact you can say that omega is equal to VA let me just check one thing. So it's VA divided by this distance. Let's say this distance is x, and this distance is y, then it is VA over x, which is also equal to VB divided by y. Okay, so you can see that the velocity of the center of the rod is, or the center of mass of the rod, if it is a uniform rod, is given by, and we can just take any one of the expressions, it's VA divided by x times L over 2. And you can go another step further and you can see that x is nothing but L cosine alpha and y is nothing but L sine alpha, right? So you could then say that the velocity of the point Q is given by VA divided by 2 times L over x, and L over x is equal to 1 over cosine alpha. So here you have an expression for the velocity of the center of the bar as the bar is sliding down with the bottom end touching with the ground and the end A rest or sliding against the wall. Okay. So this is another category of problems where we apply the principles of instantaneous center for simplifications, for getting a physical intuitive understanding of the problem, and so on. All right. Now we'll look at another case where the instantaneous center is going to be different based on different types of motion conditions. So consider the case where there is a gear and there are two guide rails, or you could say a rack and pinion kind of a setup. Okay, so this is a gear that is meshed with this upper bar and the lower bar. All right, and we are going to look into some cases, that motion cases that will emerge depending on how these bars are moving. So let us consider the case where the bar on the top has a velocity v1, right, and the bar on the bottom is given a velocity v0, right? So the idea is that this circular gear is sandwiched between these two bars, and the top and the bottom bar are given different velocities. And we are considering one case where the top bar is given a velocity to the right of v1, which is, and the bottom bar is given a velocity again to the right of v0, and v1 is greater than v0. Now since this is a gear that is meshed to these two bars, so then the velocity at the top, let's say at the point P, is going to be v1, and the velocity at the bottom is going to be v0. So if you consider this gear, you can find out the instantaneous center by joining these two velocities, because they are parallel but they are on the same rigid body, and in fact the perpendicular lines to the velocities are the same. So you can find the instantaneous center to be over here. Okay, so at this instant the whole rigid body or the gear is instantaneously rotating about the point C. Okay, now let us consider the point O, which is the center of the disk or of the gear. Now extending this idea of instantaneous centers, you can then predict the velocity of O to be again parallel, because the point O is on the same line, okay, as P and Q, where this line is perpendicular to the two velocities. So the velocity at O is going to be, let me call this V2 instead of V0, just to, and let me call the velocity at O as V0. Okay. So you can see that in this case the center moves towards moves forward. So note that center O moves forward and gear turns with omega equals V1 over PC equals V2 over QC. Right? In fact, from here you can say that because omega is equal to V1 divided by PC and V2 divided by QC, then omega is also equal to V1 minus V2 divided by PC minus QC, because they are the same ratios. So if I subtract them, the ratio is maintained, right? So I can deduce this from here, and then PC minus QC is PQ. So it is V1 minus V2 divided by PQ, which is V1 minus V2 divided by 2R, where R is the radius of this gear, or you can say 2R is the distance between the two parallel bars. Right? Now one thing that we can note here is that when V1 is equal to V2, that is the top bar and the bottom bar, they are moving with the same linear speed, then omega is equal to 0, right? But VO is equal to V1 is equal to V2. So therefore the center moves forward without gear rotating when V1 is equal to V2. Right? And that is kind of intuitive here. As you can see, if the two bars are being moved together at the same speed, then the gear will not rotate, it will move with the bar because the gear is meshed with the two bars. Okay, so this is one case where we can look at the different types of motions that are going to happen when the two bounding bars are given different types of velocities. Now another case for this, a related case, is when you still have the same setup But let's say that this point is given a velocity v1 here, the opposite direction, and this point is given a velocity v2 like this. By the way, one of the reasons of discussing this problem is to basically demonstrate that when a disk or a wheel is rolling without slipping on a surface, it does not necessarily mean that the instantaneous center is at the point of contact. It depends on what kind of velocities are being given. In this case, the ground itself, whether you consider the ground to be this or to be this, the ground itself is moving. And because of that, the instantaneous center is not necessarily at P or Q, but rather at a third point. Okay? Same thing happens over here. So let's say you have V1 here and V2 here. This is the center O. Again, we have two parallel velocities, and they are at two different points, P and Q. And the perpendicular through those two velocities are actually the common perpendicular. So we can again join the tip of the two velocity vectors, and we see that the instantaneous center now is over here at C, which is different from the center, from the geometric center of the gear O. Right? So this is another scenario where the geometric center or the contact points are not the instantaneous center. In fact, in this case, the geometric center has got a forward going velocity or a backward going velocity in this case. So here, center moving backwards. Right? And you can do similar calculations to find the angular velocity. Again, using similar triangles, you can find out the angular velocity expression if you consider V1 and V2 are given. Let me just see here. Here the angular velocity is V1 divided by PC, which is equal to V2 divided by QC, and so I can say that this is equal to then V1 plus V2 divided by PC plus QC, and PC plus QC is 2R. So here omega becomes V1 plus V2, the sum of the two magnitudes, divided by 2R. Now here an interesting case happens when V1 is equal to V2. So when V1 is equal to V2, we see that then the C, the instantaneous center, is at the point O. And so what will happen in this case is that the gear will not move, but rather it is going to just rotate in place. So when V1 is equal to V2, instantaneous center is, and you can show that VO in this case is going to be equal to 0. Therefore center does not move, but gear spins in place. So let me just separate this because this is part of this discussion. So when V1 is equal to V2, what happens is that the center C coincides with the point O, and then the velocity of the point O becomes 0, VO becomes 0. So the gear is not moving, neither forward nor backward, but it is spinning in place. So that's an interesting situation that happens. And again, this is something that you can predict. You see, what we are predicting are some of the kinematic characteristics of the gear. So we are predicting some kinematics without actually doing without actually using the relative velocity equations, without actually having to do those vector multiplications and so on and so forth. Okay, so now we will talk a little bit about the extension of this instantaneous center to motion of rigid bodies in 3D space. So it's no longer an instantaneous center when you go to the 3D space. It's you could say that it's an instantaneous axis. Okay, and so we'll not do too much math here to figure out the directions and so on, but we can give an intuitive understanding of how to figure out the axis of rotation when you consider a rigid body in 3D space. So imagine that there is some arbitrary rigid body in 3D space, and I take a point A, and let's say that the velocity of the point A is given by this vector. So what I can do is, to find the axis of rotation, what I can do is, now instead of drawing a line that is perpendicular to VA, now we are in three-dimensional space, so there is going to be a plane that is perpendicular to VA. So let's sketch a plane that is perpendicular to VA. So let's say that here is a plane that is perpendicular to VA, and right, so the vector VA is perpendicular to this plane. Now let us say that VB is a vector, is a velocity vector with a certain direction. B is this point. Then we can draw a plane that is perpendicular to VB as well. So let's say that plane is given by right now. So this plane is perpendicular to VB, and this plane is perpendicular to VA. Now the intersection of these two planes, let's say the intersection happens let's say the intersection happens here. right? The intersection of two planes is a straight line, and in this case that line is going to be the instantaneous axis of rotation. Okay, this figure may not be very accurate in terms of the orientations and so on and so forth, but essentially you can see that the extension of the instantaneous center to rigid bodies is going to be an instantaneous axis, and the way to find the instantaneous axis is to draw a plane that is perpendicular to the velocity at one point on the rigid body, and then if you know the velocity at a second point on the rigid body, to draw a plane perpendicular to that velocity and let the two planes intersect. The intersection of two planes is a straight line, and that line is going to be the instantaneous axis of rotation, okay, of the rigid body in three-dimensional space. Now this is a bit more complicated to geometrically, construct or to use it for calculations. So typically the instantaneous center discussions is limited to rigid bodies in two-dimensional space, which still covers a huge category or huge number of practical problems in kinematics and dynamics. But when it comes to three-dimensional rigid bodies, we do not use this geometric concept because it just becomes too complicated to sketch them, to predict the axis of rotation, and so on and so forth. So that's the discussion on instantaneous centers, and it's, as we mentioned, it's a very useful concept that can be used to reduce the number of calculations, because it readily gives you things like angular velocities, directions of velocities at certain points. So it can be used to our benefit in solving problems in dynamics if we understand the geometry properly. So with that, we will end this video. Thank you.